Okay, folks, so here we are, chapter 2. We finally reached the end, so I thought it would be useful to do a little summary of the chapter, of all the things we've covered, which was quite a lot. I think this is actually one of the longer chapters in the book. So it'll be useful to just touch on what we saw so that we can better help remember that and take it forward. Okay, so the chapter was all about probability distributions. So a lot of what we did was talking about probability distributions. So let's go and just make a little chart about all of this. So let's do it this way. So it's going to be chapter 2. And one of the key theme was probability distributions, right? And these, for the most part, so we could split them into parametric ones. And that's what we spent most of the chapter working on. And then there was the non-parametric approaches that we touched on at the end. So let's talk about the parametric ones first. And so we split those basically by their domain, so by the types of variables we were dealing with. So let me just draw this line down so that I can see what the boundary is of what you guys can see. Okay, so first we had, so we can go down here, let's say binary variables, things like a coin toss. And for that, we had the Bernoulli distribution. And if we were interested in the counts, so the number of heads in however many trials, we had the binomial distribution, right? And then after we talked about those, we discussed one of the first things we discussed was coming up with priors on the parameters of these distributions. So this is where we met the beta distribution, which was a way of putting a prior on, for example, the probability of the coin. We then talked about variables that had, they were kind of categorical variables. So it wasn't just one of two. You could think of them as being not, binary, but like n-ary, or categorical. It could be one of 10 items. So I don't think we even called it. I don't think we called it. Let's call this categorical. And so I don't think we actually gave it a name. Maybe we did, but the corresponding probability distribution was the multi-Newly. It could also be called categorical. But the distribution we talked about for the counts of how many of each category occur, that was the multinomial, right? And that was just exactly kind of like the analogous to the binomial, but for when you have like 10 different cases. And we talked about the Dirichlet distribution as the prior on the parameters of a multinomial distribution. So after we had discussed those, then we really arrived at the stars of the show. And this is the one that you really should pay a lot of attention to, which was the Gaussian distribution. And so this is actually, so let's be consistent here. So let's actually do it this way. So if we're now dealing with continuous, we can then say unbounded, so continuous variables that can take on a full range of values. That's where we met the Gaussian distribution. We spend a lot of time looking at how to do how it's parameterized, how to do different kinds of inference on it. What if the covariance and the mean, but you want to know like one corner of it, etc. So this was I'm going to highlight this. Super important. Definitely make sure you're comfortable with that chapter. The rest of the stuff, it's good to know that it's here. You don't have to memorize it, but the Gaussian business, it's really good to be very comfortable with that because it comes up all the time. Related to the Gaussian distribution, we also had there was a student's t distribution that came up, and that was useful for doing kind of robust inference. It was a bit less sensitive to outliers, which can be quite useful. One when the continuous variables were periodic, so let's go down here. We've got periodic. This gave us the von Mises distribution. And then I also went off piece and talked about the wrapped normal. And then talking about the Gaussian, we came up with, its various the priors on its parameters. The priors on the means were Gaussian, but the priors on the variance parameters, that gave us, we've met it before, the gamma distribution. And we also had things like, I think the Wishart and the inverse Wishart. We didn't talk about those much, but those were just, one way of kind of talking about those was as and that's the way that I've seen them, for example, especially the Wishart, the inverse Wishart, as prior distributions on the covariance or the precision. So I think that was all of the distributions that we saw, the parametric distributions, and then we talked about doing kind of non-parametric. We talked about non-parametric distributions where we just kind of learn them from the data. And remember, this was focused on this notion that the probability we assign is the ratio of the number of, we have a volume and we count the fraction of our items. So this is the fraction, and we divide it by the volume. And remember, this was also equivalent to, PV is equal to K over N, right? And that's, maybe counting, the probability mass inside a local volume. So that's the density you care about, the volume that you're now integrating that over. You're assigning a fixed probability to that volume, and it's going to be then the ratio of these two numbers, the fraction of your data set that's inside that volume. And then remember that Bishop had a really nice way of talking about this. So he said, well, our approach can be either we fix K. So if K is fixed and we're changing the volume, that gives us the nearest neighbor methods. And those can be useful because, sometimes let's talk about the other approach first. And then if you fix the volume, that gave us the kernel density estimators, right? And one issue with them was that sometimes they would, depending on your kernel, they would assign 0 probability to some locations. So with the nearest neighbor method, you just expand your volume until you have the number of K points you're after in that data set. So at least you don't run into that problem. Good. So that was basically all the probability distributions, I believe. Oh yes, and then so now that we kind of discussed all of that, there were a few others. So there was the mixture of Gaussians, which is also very important. The mixture of Gaussians, which gave us a bit more flexibility. That was also very good. And then most of these, except for this one and the mixture of Gaussians. The rest of these guys we saw were they can be thought of as, well, you can view them in a unified way by seeing them as members of the exponential family. Remember, the exponential family had a parameterization in terms of natural parameters, but it had this really cool property of having the sufficient statistic. And that was really interesting because what's the best way to describe it? So it basically says that it summarizes data in as many dimensions as the parameters, even if you have an infinite amount of data. So, finite dimensional summaries of the data. And these are lossless summaries, right? So, for example, if you're trying to figure out, the bias of a coin, you don't need to keep the whole history of the coin tosses. You can just keep the fraction of tosses that have been heads, and that's all the information there is. And so the exponential family was the only one which had these finite dimensional sufficient statistics. And it had it also had a notion that we came across a few times. They also had very nice, conjugate priors that we could they always had conjugate priors that I think were in the same family or something like that. So they've worked very well with the conjugate priors, basically. So this was kind of a unifying approach to most, but not all. So the students T and the mixture of Gaussian were not in that group, but the rest were. So that's what we talked about. Another theme that we talked about throughout the chapter was this notion of kind of inference, right? So now we have probability distributions, we want to guess their parameters, not guess, estimate ideally. So how do we do inference? And there was maximum likelihood. So that was, so this was, you're maximizing the likelihood function, P of, x given theta. And then there was well, it's not quite Bayesian, but let's say a bit more Bayesian. So you bring in a prior distribution. So that was, let's say you want to maximize, or not even maximize. You actually just, to be fully Bayesian, you just keep the full distribution, right? So this is like, just give me the prior distribution. And remember, this requires times P of theta. So then we needed, we needed priors. And then we got to, conjugate priors were a topic that came up a lot. And the conjugate priors were such that the posterior would be in the same family as the likelihood. So that you essentially ended up just updating the parameters of this same family, which was very nice. And so if you can do that, it's often very useful to do. Makes your life a lot easier. And then we also talked about one other aspect on this point was doing, inference, doing this in batch, so using all the data, or sequential. So this came up a few times. And then once we kind of hacked our own sequential estimation procedure, but we saw that there was actually a more principled way of solving the sequential estimation problem. So that was where we came up with, where we encountered I wanted to highlight it, the Robbins-Monroe algorithm for maximizing, which we applied to coming up with sequential algorithms for estimating our parameters. So that was that. And then in terms of, so I think that's basically all we covered in the chapter. It was quite a bit. I think in terms of techniques, I think the main, the bits you should really be familiar with are really be very comfortable with the Gaussian stuff. It's going to come up a lot. In particular, with relation to the Gaussian, remember we had this notion of, where am I going to find room for it? I'll just put it down here. So remember there was completing the square. This is a very, so maybe if we have, I think, so let me actually add a little section here, which is called techniques. One of them, this Robbins-Monroe, is quite useful. The other one is, completing the square. It's even more fundamental. So make sure you know how to do that. But I think as a whole, don't worry too much about memorizing all of these probability distributions. You'll get a chance to come back and revise this stuff later on as it becomes needed. Just know that they're kind of available for you to use, and indeed be quite good with the Gaussian stuff. I think the notion of the exponential family is also, I think, quite powerful. I don't know if we'll use it much in the rest of the book, but that can also be kind of a unifying approach, if you prefer, for keeping all this stuff straight. Good. So I think with that, I'd like to finish chapter 2. I think it was quite a long chapter. It took a few months to finish, but we have done it. So give yourselves a pat on the back if you've been following along the whole time. And I'll see you next time to start chapter 3. Bye.